Hello, everyone. Thank you so much for joining us. Today, we have a pleasure to have Eder Martioli in our weekly colloquium. Eder is a permanent researcher in National Laboratory of Astrophysics in Brazil, and also he is associated researcher here in IAP. Indeed, I continue. Yeah. So indeed, he passed 3 years here as a postdoc here between 2019 to 2021 it was a COVID time. He's the part of the scientific team of several worldwide instruments, including SOPHIE, SPIRou, Gemini, and also TBL, which is a telescope in south of France. His research is focused on detection and characterization of the planet, and today he will share with us his latest research, including those collaborative projects with IAP. The stage is yours.
Okay, thank you, Neda. So, thank you, everyone. Thank you for inviting me. I hope you guys can hear me well. Everyone can hear? Okay, good. Thanks for, in particular, I'd like to thank the group, the exoplanet group at IAP, who invited me to come here to spend 2 weeks. I'll be here next week as well. And to give this talk, it's a great pleasure to be back to IAP, because I spent 2 years here as a postdoc in the COVID times. But it still was a very productive time, very nice. And it's an excellent environment here for research. And I will show you today some of the results of work that's been done here in collaboration with the exoplanet team, and also with other scientists of the French community and worldwide, including other telescopes and other groups. So this is a talk about exoplanets, but I will concentrate my talk on the exoplanets and a specific kind of exoplanets, the exoplanets that transit their stars. So exploring the legacy, because now we have so many planets detected with transits. I don't know, a few years ago, it was just 1 or 2. Now we have thousands. So we can explore this legacy that's here, because they're very important ones. They are the ones we can extract more information. We can extract more physical information, and we can infer other things from these planets. So first, why exoplanets are important? Why do you care? First, they are located, they are planets that are located outside our solar system, such as those orbiting other stars. Could be floating planets, could be orbiting brown dwarfs, for example. The exoplanets, they contribute to our understanding of how planetary systems form and evolve. So this is a piece of information that we need to learn the planet formation scenario, the planet evolution in an universal context, not only solar system. They are places that are very intriguing and complex, because that's where we have the range of pressure and temperature, where you can have very complex chemistry. You form molecules, you combine molecules into liquid, solid, gaseous. So this whole mix of stuff makes these places very interesting. So that's something that's very interesting about planets that we want to learn. What kind of conditions we can find out in other places in the universe. And they can also serve as messengers. Planets can be used as probes to learn more about the environment where they've been formed, or even about the star that the planets orbit. So how is the inventory of exoplanet today? I show here the main techniques and the status of how many planets have been detected by each of these techniques. Some of them, like astrometry, is still only 3 planets have been detected, but astrometry have also been used to learn more about planets detected by other techniques. So some of these techniques, they can be used combined. And that's actually something that I'll explore in my talk, because we use multiple techniques to observe the same system. Imaging, for example, about 100. Microlensing, that's a different technique, about 225. Radio velocity, about 1,000. And transits, or transit time variations, that also needs trans to detect them, about 4,000. So as you see, the technique of transit that was in the past, a very people were thinking, oh, it's not likely to find many planets because the probability is lower to have a planet that crossed in front of the star. But it turns out to be one of the most useful techniques. And it's good because we need those planets to learn about the physics of the planets, as I will show you later. In this plot, we see the distribution, the mass period, orbital period, so in this orbital period and planet mass of planets. And in colors, you see different detections by different techniques. So in green, that means the closest ones to the star are the transiting ones. And as you get further, you find more and more radio velocity planets. It doesn't mean these planets in green, they hasn't been detected by radio velocity. They also, some of them, a lot of them have also been detected by radio velocity, but the first detection method was transit. And in other colors, you see the other techniques. The interesting thing on this plot, you see, first, we're lacking planets on this side of this plot. That's mainly because the techniques, they're limited. Their sensitivity doesn't allow us to detect planets in this region of the plot. But that's not true for the other side of the plot. As you see different accumulations of planets in different parts of this plot. As I will show you, there are physical reasons for this to happen this way. So how is it the galactic distribution of planets? Or at least the galactic direction, right? Because we're not seeing in depth, we're just seeing in the plane of the galactic plane. Again, the colors represent different techniques. Some of these techniques, like the transits in red, you see some accumulations, which are for example, in this accumulation is the Kepler field. And for microlens, you see an accumulation here, which is the galactic bulge, where you have most likely the microlensing events to happen. And some other techniques, like in green, the radio velocity, you see the spread over all the galactic plane. So one of the main results that came after the Kepler mission that detected thousands of planets, transiting planets, was the exoplanet occurrence rate. So we wanted to know how frequent planets are in our universe, or which kind of planet is more likely to form or to exist than other kinds. So, and you can see this in this plot. You probably can't see the numbers, but I can tell you that the red means low occurrence rate, and green means higher occurrence rate. So this is a planet radius in the y-axis and orbital period in the x-axis. That means larger planets with shorter periods, they're less likely to occur. And the other way around, longer periods with smaller planets, they are more likely to occur. So how dividing this now into categories that we can know by their names, Earth-like are those planets in below, the super-Earths, the mini-Neptunes, Neptune-like, and Jupiter-like. So that's how they are distributed, and in this direction, it's the distance from the star or the orbital period. What's interesting here is super-Earths, for instance, we don't have a super-Earth on our own solar system, but there seem to be the most likely, the most frequent planet in the universe. So we're just lucky to, or unlucky to not have a super-Earth here in the solar system, but they're very common to find in other systems. So these kind of things are things we learn from exoplanets. here's another version of the same plot, but dividing by spectral type. So we can ask our questions what if a lower mass star has more planets or form planets more easily than massive stars? And the answer to this question is yes. M stars, which is the plot on the top here, are more likely to form planets for all range of distance than more massive stars. So that goes. But if you look, one detail of this plot is that is the error bars. The error bars on M stars is larger than for massive stars. That's because we don't detect as many planets on M dwarfs than we can detect for other stars, for instance, FGK or solar type stars. Why? Because it's more difficult. So that's also part of my talk. We'll explore this kind of challenge to detect planets around the M dwarfs, because we need to learn more. We need to decrease those error bars. We need to know better how are the planets formed around these lower mass stars. What about metallicity? Well, metallicity, there is this work that it's being realized since the beginning of this radio velocity service, that planets, larger planets with higher metallicity, they're more frequent, or stars with higher metallicity are more likely to have planets. And that's what this plot says. But what about if we change the mass of the planets? Because in this first service, we only had massive planets. They were most easier to detect. But now, if you look at this work of Narang, 2018, this is the average metallicity per planet mass being. So if we look at these massive planets, it's okay. It's higher than it's a supersolar metallicity. But if you go to smaller planets, it's subsolar. So that means it doesn't matter. The metallicity is not important to form smaller planets. So smaller planets can form even in low metallicity environments. So they don't seem to follow the metallicity trend that is the same as. But as you can see, there is also a big dispersion there. That's because smaller planets are harder to find, to detect, to follow up. And also low metallicity stars, they're also not as frequent because those are the ones outside the disk and so on. Looking at the planet population, we can learn things about the planet formation. One important result that came out of this big service, and in particular transiting planets, is the detection of this small planet radius valley, which, when you look at the population, the planet size and stellar intensity, which is similar to orbital period, you see there is accumulation of planets in two places, but there is a gap in between, and this gap is being measured. And it seems that this, if you run simulations and if you run the models, the position of this gap, or the division between these two populations, can be related to some different process of formation. And it's mainly caused due to photoevaporation. So when planets that are gaseous or they have a gas envelope, they migrate inwards towards the star, they get more radiation and they evaporate. So they become smaller because only their core is left exposed. But how this process happens, it depends on the separation of this population. And there's another interesting feature on the distribution of planets. In this case is the mass period diagram, where you cannot see or cannot find many planets in this region. And this is the evaporation forbidden region. This is the region where planets if they migrate in with that mass and that distance from the star, they will likely evaporate and they will become less massive planets, and they will not be in this region of this plot. So this is so-called the subjovial Neptune desert. So how is our incremental knowledge of planets becoming? You know, planets are common. Small planets being more frequent. Lower mass stars can form planets more easily, in particular smaller planets, and they have a lower dependence on the metallicity. The planet evolution is affected by the initial size, the orbit, stellar type, chemistry, one of the boundary conditions. Their fate depends on how much they evaporate or they can lose their mass, on the stellar type and the chemistry of the planet. And the better we understand, we can understand better this planet formation scenarios looking at the planet populations, okay? So, and now moving to the transiting planets. What's important in these transiting planets? Why they are so important? Because we can get parameters, we can measure the parameters that is not, some of them are not possible with other methods. For instance, the planet mass, the planetary radius. Well, the planetary radius is measured right away from the transit method. For the mass, you still need a follow-up on radial velocity because you need to measure the orbit. But you can also get other things like the spin-orbit obliquity, which is the angle between the orbit, the plane of the planet, and the spin axis of the star. So this is related to the formation because they're supposed to formate in the same plane as the disk, but as they evolve, they could have dynamical interactions which will make them go out of this disk. And the way to probe that is by looking at the spin-orbit obliquity. We can also measure the composition, atmospheric composition through transmission spectroscopy. And transiting planets also help characterizing the star. We can learn more about the star from the planet, as I will show some examples. So the transit. Here is a real transit. That's the transit of Venus transiting our sun. But that's a real image of what we see in our solar system, but just showing an illustration, an example of what we see in other systems as well when you measure the transit. But it's exactly that, right? The planet passes in front of the star, there are spots, the star has this not uniform illumination because there is a limb darkening effect. And when even in this, here you see a thin atmosphere of Venus that is illuminated by the stellar light. So that also happened in transiting of exoplanets, and that's how we get to learn about these atmospheres. The transit light curve is a powerful technique to measure the transit and the stellar parameters. This is an example. This is showing the plot. How is it? You measure the brightness of, do like a time series of the evolution of the brightness of the star during the transit, and then this shape, you can model this shape, you can obtain from the depth right away, the radius of the planet, and other parameters, orbital parameters as well. So the impact parameter is an important one as well, because you can see the shape changes as you change the impact. What they call impact parameter is how far the planet is transiting from the center of the stellar disk. So if it's transiting very far on the edge, it's a grazing transit. It's almost the shape of an eclipsing binary when you see the light curve. But when you in the middle is more like this bottom here, and you see it varies depending. So we can measure that quantity. For the limb darkening is also an important stellar parameter, but that can be measured from the transits. Here I show you several different limb darkening laws that we can use, and you can probe those laws if you have a precise enough light curve from the transit to measure. In particular, if you have light curves in different spectral regions, like in different filters or in different spectral channels of spectrographs, you can measure the spectral dependency of this limb darkening, which tells us a lot about the star as well. The transit depth changes with the stellar type. If you have a smaller star, like an M dwarf, for the same planet, the transit depth will be deeper than when you have a more massive, bigger star. The transit depth also relates to the planet type. In this case, you see the disk of the planet will tell you how much depth you have in your transit. So if it's larger, and you see here different planets, for instance, the one above for 1 Earth mass and below, all of them are for 5 Earth mass. And even if you change for the same planet mass, if you change the composition, you change the size, but it's a weak dependency. You still need more information to get this. For instance, the mass could give you, with the combined to the radius, you get the mean bulk density, and that's how you can infer some internal structure of planets. So, and that's where radial velocity comes in, because it's a good technique to combine with transits. Most of the transiting systems, they can be followed up by radial velocity. And radial velocity is just, instead of the same planet that transits the star, they also have a gravitational effect on the star, because their center of mass is not in the center of the star, it's offset. So the star wobbles. And then with spectroscopy, you can measure these wobbles, and you can combine the transit equation with the radial velocity equation. They share the same orbital parameters. So we can do a global fit of these two data sets of the transit light curve and the radial velocity to obtain all the planet parameters. In particular, the mass is the planet mass is a parameter that is obtained when you apply the radial velocity data as well. Because without radial velocity, you cannot know for sure the mass. And you could also include astrometry. Astrometry in this case would be to measure not, it's always hard to do this, huh? Okay, so astrometry, you would measure this movement of the star. We have a case where we applied astrometry. We use Gaia data to constrain the mass of an exoplanet that we detected by radial velocity. I'll show you this example. And what about the Hall-Stammer-McLaughlin effect? That's when you measure a transit with spectroscopy. So you do precise radial velocity follow-up or monitoring of your star during the transit. And what you see, while the planet's transiting one hemisphere, the light is coming towards, the star is rotating, right? So that the light, this hemisphere is approaching us. So the light is blue shift, and then when you have the receding hemisphere, it's red shifted. And then you have a lack of that part of the transit. You have a lack of light on that, so you see a signal in your radial velocity. So an induced signal in radial velocity, and depending on the alignment between the stellar axis and orbit, you can get different shapes of this, and you can measure that. So the parameters involved in this measurement is also the same orbital parameters. In addition, we also have the lambda with data obliquity, and the V sinus I, which is something sometimes hard to measure with spectroscopy. So we combine all these multiple techniques: photometry, astrometry, polarimetry, high contrast imaging, high resolution spectroscopy, spectral polarimetry. Using these instruments, TESS, SPARC4, SOPHIE, SPIRou, MAROON-X, SALUPEC, SPIRou, SPARC, and AST in Gaia, to learn about these planets. So, this part of the talk now, I will show you some of our explorations of exoplanets. So some systems we explored, we detect, we followed up to learn more about this exoplanet. So the first one, it's a very interesting one. It's a very young system. This is AU microscopy. At that time, there were two transiting hot Neptunes detected. We contribute to the detection of this planet see here using TESS data. And this star is so young. It's an M dwarf, about 20 million year old. It still has a debris disk around it, which is detected here by the JWST. So in these two planets, it makes them the youngest transiting planets we have knowledge. And it's a bright star, so it's a star that is easy to follow up. It's a nearby star. So it makes an interesting system to learn about planets in their infancy, in their very early stages of formation. So here's the data we use to detect these planets. So the problem is when the star is very young, like a UMIC, you have a lot of stellar activity. And you can see in these two plots below, the one on the left, you can see the flaring activity that we had to model together with the transits, and also photometric variability due to stellar rotation, the modulation with stellar rotation. So all this has to be modeled together to be able to see those plots above, which are the transits on the left of EUMIC B, on the right of EUMIC C. So those are the transits of these new planets that we studied in 2021. Then we use the near-infrared spectral polarimetry, spectral polarimetry infrarouge, the SPIRou instrument at the CFHT telescope on Mauna Kea. It's a high-resolution, stabilized near-infrared spectrograph and polarimeter, so we can do spectral polarimetry as well. And we use this instrument to follow up a UMIC. And the first thing we learned about the UMIC was that this planet, the UMIC B, the closest one, is actually aligned with the stellar rotation. That means in this time of this planet's life, which is very early, it's still aligned with the disk. It's not off, or the interactions didn't go so strong that made it to go off the disk yet. And then we use the same data to learn more about the magnetic activity in a UMIC, which is represented in this plot here. Here is the LSD profiles, the least square deconvolution. In this one above is the line profile, the flux. And this one in the middle is the polarimetric profile in the lines. So it's all the lines, or a list of lines combined into one single measurement. In this mean profile, you can see the Zeeman effect, which is the split of the two Zeeman lines that has polarizations, opposite polarizations. So that's why you see one to the top and the other one to down. It's like an S shape. So it's a clear detection of the magnetic field on the stellar photosphere. So we did that, and we followed up during the transit of UMIC B, and you see the magnetic field is actually changing during the transit. But that's because of stellar rotation. As the star rotates, the spots, the UMIC probably has large, huge spots, and those spots, they have different magnetic fields. Then they are being hidden behind the star, and you see the magnetic field changing during this transit. So we also use the SPIRou data to detect the radial velocity, because SPIRou is a very stabilized spectrograph. So we can use this to detect the radial velocity of a UMIC. And of course, a UMIC also has a lot of variability in radial velocity, which is larger than the planet signal. We had to model the stellar activity together with the planet, but we were able to measure with a 3 sigma confidence the mass of UMIC B at the time. And using more and more and more data, each one of these data points is a spectral point or a measurement. We followed it for several years. And we found that the unique B and C is confirmed with a better accuracy of the mass determination. But we also found some evidence, which is not confirmed yet, but for a planet E, another planet. And I should mention also that EUMIC also has evidence for another planet D that's not mentioned here, because it's been detected by transit-time variation, TTVs. But the ones confirmed are the ones with that transits, because on these active stars, it's very hard to confirm planets, in particular small ones. What about the composition of these two planets, the main ones? If you want to know the composition of planets, you can do it or you can estimate it for transiting planets, because you know the radius and you know the mass. So you go to the radius mass diagram, basically placing, depending on the density of this planet, it has different models that can tell you what kind of composition that planet has. For sure, planet B is a gaseous planet. Planet C, we don't know. It might have a very large envelope of some more heavy elements or molecules, like water, for instance. This is another planet that we studied, TY 1759. This is a transiting planet detected by TESS. And then this is the TESS light curve you see there. We followed up this system also with SPIRou, with an infrared spectrograph. That's the radial velocity below, where you detect the variations. And we measure the radius, the mass, the density, and all the characterization that we can do with this kind of a planet. In this plot above here, you can see in green is the habitable zone, the classical habitable zone of the system. As you can see, it's much closer than the habitable zone. It's in a region which receives a lot of stellar radiation. That means this planet might have some evaporation effects, or an extended atmosphere, an inflated atmosphere that could be potentially followed up by transiting spectroscopy. From this system is not as young as EUMIC, but it still has some magnetic activity. We measured the magnetic field. As you can see, we also detected the Zeeman effect with the LSD profiles. And from these measurements, we measured the evolution of this magnetic field. And again, we found the modulation, and that's how we learned about the stellar rotation. This star rotates at 35 days. And this helps us to learn more about the planet, because sometimes you can find a signal that is very close to the stellar rotation. But if you know the stellar rotation, you can rule out those signals, or you can say, okay, these signals are for sure stellar rotation, and we can now focus on the planet signals. So we can model this together and be able to get more precision on the planet parameters. Here you see some magnetic maps that can be done with this kind of observations of the magnetic field in several rotation stages. Then you can reconstruct the magnetic field at different, in this case, at different epochs in 2020, 2021. It didn't change very much, but still you can see some changes. Again, we'll go to this radius mass diagram to see what's the composition of this planet. And as you can see, it's not very far from EUMIC B. It's about the same region with a large uncertainty, as you can see. But it's for sure a gaseous planet, a Neptune-sized gaseous planet. This is another planet that we also followed up with SPIRou. In this case, it's a little bit smaller than TY 1759. The interesting thing about this one, now I go, you already know what the technique, you know how we do it. So we use TESS and SPIRou data to detect it. And we go right away to this plot, because this is what makes this system interesting. As I told you before, by the distribution of planets in this radius period diagram, you can there was the radius gap, right? The photon gap, which is the gap between the two populations. But there are planets in this gap, and those planets are called what they call the keystone planets, because they're the ones that are in the region with not many planets. So we don't have many planets on that region. They're in a region that is probably more, they spend less time in their evolution, or they are more affected by evaporation effects. So that's why they become important, because they're transition planets. And in this case, this is done in work by Fabian Kiefer, myself and Guillaume and other collaborators. We found this in exactly that region of the gap. And this other one, that these three planets were studied about the same time using same technique. So again, TESS and SPIRou. But this one is a very low mass. And what's interesting about this planet, as you can see, this orbit is, you probably can't see on the screen here, but it's inside the habitable zone. And showing here in perspective, these three that I just showed, the gaseous one, the 1695, which is in that transition region, and 1452, which is lying right where you expect a lot of water and a lot of heavy, when I say heavy, it's not only hydrogen and helium, it could be more molecules formed in the atmosphere because of this density. So it becomes just an interesting planet because it could be one of those ocean worlds. So that we applied for time at JWST trying to get more information about this planet, but we still need to improve the mass determination to decrease those error bars. So we try to continue observing from the ground before we can go to space and learn more about this. Another interesting one that was in basically the same time was this TY 4860b, which is not a water world or something fancy like this, but what makes this very interesting is because it's a giant planet close to an M dwarf. It's very rare to find this kind of a giant planet inside. It defeats planet formation because if you look at other populations, you don't see many planets in that for that parameter space. So now I move to planets around solar type stars, or stars that are very similar to the sun, that we followed up with TESS, or we detected with TESS, but followed up with SOPHIE spectrograph in South France at OHP. These two planets, TY 2141 and 1736, they are around what we call the solar analogs. Why is it important to observe planets around solar analogs? Well, first, there are stars like our sun. So we expect systems similar or can compare to the solar system or the solar-like stars. But the other important thing is, if you remember the equations, there are always stellar parameters in those equations. So you depend on the precision of stellar parameters to obtain precise measurements of the planet parameters. And which kind of star will we know better? We know better the stars that are similar to our sun. So in those stars, the planet parameters are actually more precise than in other stars. Although sometimes they're more difficult, as I showed you, the transit depth on M dwarfs is larger than on solar type stars. But anyway, these two stars, similar to our sun, they're very bright ones, magnitude 10 and 9, about the same. So they're solar analogs, so they're very similar to our sun. All their parameters are very close to our sun. So I'll go straight to the detections. We detected in radial velocity and the transits with TESS. And here are the planet parameters. Here's the size of the planet compared to Earth. So they're not very they're not very large as Jupiter, but they're definitely larger than Earth. This system, the 1736 in particular, we detected when we were studying it, we started with the transits, so we wanted to follow up. And we learned that this is also a binary system that's been detecting these fringes that you can see in high contrast imaging. And also when we fit the SED, we didn't get a good fit with only one star. When we include another star, we get a perfect fit. So we confirmed the detection of this binary, this K star around this solar type. But the binary, the second component is far enough that doesn't interfere with the planets. So the planetary system, we can detect it alone around the main, the primary. And as you can see on that radial velocity curve, we are searching for this guy here, the plot on the top, you know, the 7-day signal, because that's the one we detect with TESS. But then we found that huge variation. Okay, there might be another planet. We did continue following up for 3 years, and we detect this large planet, a huge planet. It's 8.7 Jupiter mass compared to the other ones, Jones 12 Earth masses, which is just a fraction of Jupiter mass. So that's it. The system has an inner planet which is small, Neptune size, and it has this large, very supergiant planet outside. So the interesting thing is that this supergiant planet is orbiting in the habitable zone of that solar-like star. But of course, this is the supergiant, it's almost a star, but it could have moons, who knows? But still, so it's in this. And we identified other systems similar to this one to compare, and it seems to be like a not very rare, but there are some other systems that share the same kind of configuration. And that's the location in the radius mass diagram. They're mostly around the same. As you can see, the error bars are smaller than the ones I showed before, because we're talking about solar analogs. And here in this plot, you see this star illumination fraction, or the effective temperature. So solar temperature, and 1 means Earth. So this one, 1736C, is at the same illumination or same irradiation, stellar irradiation as what Earth receives from the sun. So the habitable zone. And that's the guy we measure the mass using Gaia astrometry. So use Gaia astrometry because we want to detect it in radial velocity. Then we use the Gaia astrometry to constrain the mass of this planet as well. And we have several other planets around solar type stars that we detected, and they're all published in these papers. But yeah, I won't talk about all of them. So now more for the future, more like new things we're doing. We're studying planets in different galactic populations, because as I showed in the beginning, there is a dependency of the galactic or of the metallicity, and as you know, different galactic populations has different metallicities or different chemical composition, and how does this affect planet formation? So we're interested in looking at these different places in the galaxy to learn about planets. And one of our projects is to follow up TESS planet candidates that are in halo stars that are members of the halo. Because of the orbits, we can in chemistry, you know they're from the halo, but they're passing through the disk, so they're close enough that we can detect the planets. So they could be from extragalactic origin, and that would be a detection of an extragalactic planet or a planet around the star that has origin from extragalactic. And usually we place this in this plots to know which population it belongs. And then that's how we do our target selection. We also look at the chemistry to know if it's a halo like chemistry. And we use this spectrograph, the MAROON-X spectrograph from Gemini North, to follow up because it has enough precision to detect this kind of planets around this star. They're usually not very bright, but bright enough, some of them, a few of them, to detect with Gemini, the 8-meter telescope. And within this contest, we detected this guy here. But I can tell you in advance, this is not an extragalactic planet, and it is not even from a thick disk population. We thought it was from a thick disk population because it was in the catalog. But then with our follow-up, we learned that it's not. But it turned out to be a very interesting planet because it's in the desert, in the subjoven desert, that region forbidden. And here you can see that it's not. We would expect this to be a thick disk planet, but even thick disk is not. It would have to be in the gray line, gray area. Halo ones are the blue ones. So it's most likely from the plane, from the thin disk population. But here is the TESS data detection, the radio velocities, and the follow-up. We also follow up this with SPIRou, and it confirmed our detection with MAROON-X. We did some spectral analysis. So the important thing here is it's in between these two big populations. If you go to this mass period diagram, again, you see this, the subjoven desert, which is that region, and the planet is within that region. And it's within that region, right in the transition between these two populations of exoplanets. Below are the super Earths, and on the top are the hot Jupiters. And if you use this, we can probe the photoevaporation status of this planet, TY 3568. We plot in this energy diagram. So planets should not be below those lines, otherwise they will evaporate because it's unstable. And it's right on one of them, so it's in a stable region. But still, if you look at these two populations, it's still in between. You can't tell whether it belongs to the sub-Neptune or super Earth population or to the hot Jupiter ones, because it's lying right in the edge. So it fits. We don't know. Could be an evaporating planet, but could also be just some planet that has some specific characteristic that allows it to be in that region. So now our new ventures, we are using Ghost spectrograph, Gemini South. It's a new spectrograph, high resolution. It's not stabilized, but it has a very good throughput and also a very good line profile stability, not at the level to detect radio velocities. But what we did, right in the science verification run, we observed this system here, which has a planet, a hot Jupiter detected. And in this program, Ghost allows you to observe two targets at the same time. It has two IFU, which can place a star in one and another star in another one. So two fiber bundles that goes into the spectrograph. We put our target in one bundle and another star, a field star, about the same magnitude, same spectral type, in the other bundle. And then we observe, and then here you see the CCF, the cross-correlation function that we get from all the lines. As you see, the two are very similar ones. So we can use, since it's not stabilized, but you can use another star as a reference to measure the radio velocity shifts of our target. And we managed actually to detect the Rust-McLaughlin effect on our target using this technique, because usually people use reference in the lab, iodine cell, or even the atmospheric telluric lines, or Fabry-Perot. We didn't use any of that. We just use another star as a reference, because it's simultaneous observations, and you can see the Rust-McLaughlin effect, and even the Doppler tomography map we could do for this planet. So in this is another instrument, a new one also. It's a multi-band photometer and polarimeter at Observatório Pico dos Dias, a Pico dos Dias Observatory in Brazil. And this telescope is a 1.6 meter. And this is the instrument here with 4 simultaneous channels in the Sloan bands. And we're using this to detect transiting planets, characterize planets with their transits, and learn more about the stars. So this is one result of it. It's not published yet. It's just a result that we obtained from our campaign this year, because we were commissioning this instrument last year, and now this year we are starting observations. The first year is being offered to the community, and we observed this WASP-B, and as you can see, you can get very good precision in the 4 slow-on bands for the transit. Here's the fit to this filters. You can see the shape changes because of the limb darkening change with wavelengths. And we can see like color curves, light curves in green. I just showed the ratio between the transit fit in one band with respect to the other. But in orange is the same thing, but the measured one, which I fit an interpolation, and you see we can detect those differences to characterize the limb darkening and the stellar parameters. And we also have the polarimetry mode, which also gives a good photometric precision, but also a time series of polarimetry in the 4 bands. But what we can do with this polarimetry, there is an expected signal when you have a transit of the planet. It breaks the symmetry of the star and induces a polarization. However, this polarization is of the order of 10 to minus 5, 10 to minus 6, and we don't detect it at this level. Our variability is is a 10 to minus 4. So still, we can try to go further, we can improve our techniques, but it will be very hard to detect polarization that's predicted at this level. But if we could learn more about, in particular, planets that are grazing transits. So to finish, our perspective is to have a few systems that we're studying. We are doing this survey with Spark 4 to prepare for a larger survey, perhaps observing stellar clusters or young stellar clusters or more mature ones to detect more transits around these stars. Oh, thank you.
Thank you so much, Eder.
Yeah, thank you.
Any question?
Thank you very much. I have a question regarding 2 of these planets. So I noticed the number TY1736, TY1452. And for those very interesting planets, one in the habitable zone, one is water world, are there some prospects for observation of the atmosphere using spectroscopic transit?
Yeah, as I said, let's go to the first one. This one, the water world, right? So this one, TY1452, it's an interesting one because, of course, it's in the region of the planet mass diagram that it's very likely that it has a structure. It's not gaseous and it's not solid. It's too big to be only solid, and it's too heavy to be only gas. So it must have an atmosphere with some important or interesting molecules. For instance, could be lots of water. So that it would be very interesting to follow up with transiting spectroscopy, it's for sure. But when we applied for JWST time, the Canadian team, Charles Cadieux is the PI, he got an answer that you still need to improve these error bars. It's too large, in particular the mass, you need to follow up with radial velocity for a longer time or better precision to decrease this, and then you'll be sure where you are in this plot to make a point that is really an interesting object to follow up. So that was where it stands. But of course, this would definitely be a very interesting planet to follow up. The other one is 1736. Yeah, let me show you I think this plot is a good one. As you can see, the transit is very shallow of the transiting planet. It's very hard to detect, even with dozens of TESS observations. We still detect it with it's there for sure, but it's very hard. So to do one observation of the transit to detect atmosphere, it will be very hard. For this one, for the inner one, for the outer one, it doesn't transit. It's a giant planet in the habitable zone, but it doesn't transit. Although because it's very big, it could have a significant emission. But yeah, it's an old system, so I don't know. It cannot be detected by spectroscopy, unfortunately.
I had a question about the estimation of the number of exoplanets in the galaxy. Current estimation is there is some.
The number of exoplanets
in the galaxy, in the Milky Way, I mean.
What do you mean the number of exoplanets?
I mean, you said that about 5,000 were detected, but probably there are far more than that. So like we can estimate star population.
Yeah. Well, I don't know if I'll be able to do it. I'll go all the way to this. I won't do it here, but maybe you can do it. You can see the fraction of stars with planet, or the probability of a star having a planet for each kind of planet. And then you have for each stellar type, and you can do the calculation. I don't know, a few percent, like each star has 2-3 planets. So you count the number of stars and you multiply by 2-3. So that's the amount of expected number of planets in the galaxy. So 100 billion, I don't know. I have to do the math. But it's very common. That's, I think, the main point. And because in the past, we didn't have an idea how common they were, and now we know. So now you can, for example, in this survey that I mentioned that we are planning to look at in the stellar cluster. So it wouldn't make sense to search in a stellar cluster if you don't know the occurrence of planets. Now that you know, okay, so you assume some distribution of orbits, and you have a probability of transits, and then you propagate to the number of stars you are measuring, and the magnitude, the sensitivity, and then you can expect or give a number of the expectation of how many planets we detect with the survey. So that's the way to put it.
Any other question? If not, I do also one question.
Clement?
No,
Clement,
go ahead.
So in one of the plots, I think it was a few slides further, you have a plot. Yes, exactly this one. So I was wondering if you can comment in the curve, because it looked like with the metallicity and mass, then is mass increasing, also metallicity is increasing, and then in some point there is a curve. So I was wondering if you can comment on it and why the physical reason it has a curve.
Well, the physical, well, first, if you look at the plot, you see the error bars are very large in that region for larger mass. And besides, you are already on the Braundorff regime, and there is a Braundorff desert there. So there's already a lack of objects in that region. So I think this plot should be read, I think, up to 10 to the 3 Earth masses. Further than that, you were talking about the different physics, different formation paths, because it's formed by segmentation, not by disk direction. So but still, it's the region that is between. That's the region we don't know much.
I can. Thank you. So I have several questions, but maybe one is, can you comment on how spectropolarimetry enabled to understand and control better the impact of stellar activity on the characterization of planets, like how helpful it was, and linked to that, the second question is, how many planets can we, for example, let's take the TESS candidates or take TESS planets. What is a fraction of the TESS planets that we could imagine we can follow up with polarimetry?
Okay, so for your first question, basically what we see in polarimetry is this. But this is a very strong signal in polarimetry. Normally, you won't see as strong as this, or normally you won't see it at all. So you won't get too much information from polarimetry. But if you do have a magnetic field, and if you do measure that, as you can see from this plot, the magnetic field modulates or the rotation modulates the magnetic field that you measure. And it's very precise. This is just a piece, like a 5-6 hour monitoring. But if you monitor it for several weeks, you won't be doing this continuously. You'll be doing it one by day. But then if you are close enough that activity didn't change, the structure of activity didn't change, it must be done within the same weeks or a month. The magnetic field will be modulated with rotation. So that's a very important information when you have activity, because you don't get confused when you are detecting new signals. As you can see here, the amplitude of the activity signal in radio velocity is very high. This is a very active star, a young one, but the problem becomes worse when you get a not so active, a less active star, because it mixes with the same amplitude as the planet signal. And then you don't know. And that's where the spectropolarimetry helps, because it will tell you, okay, this signal I found here, and you go in the periodogram and you see a peak, and you find, okay, this is a very periodic signal. And you go to the polarimetry magnetic field. Planet has nothing to do with the magnetic field, that it won't change the modulation. And you see the modulation, the same peak. So that's it. This is rotation. And now that's how it helps. But it won't actually help characterizing the planet in itself. Like, it won't give physical information of the planet. It will just help to rule out or to clean the activity signal. I think that's the main one. Or how many systems can be measured with polarimetry? It depends on two things. First, it needs to be bright enough, of course. At least for CFHT, it's a 3.6 meter telescope. We can go up to magnitude, I don't know, 9, 10 in age. Maybe not that far. But yes, it depends on the magnetic field. If it has a strong, like this one is very strong, it's very easy to detect. In this one, it's not so strong, but we can still detect, and we can detect rotation. But some of them, like, we don't even detect. But it's still, even when we don't detect, it's an information, because you can tell, okay, the star is not active, and we can trust more what we find for the radio velocity signal.
Thank you so much.
Yeah,
any other question? If not, let's thanks again, Eder.